Good morning, everyone. Today I will present our research on exploring the effect of different measures on thermal resilience, implication for HVAC design and energy use. The objective of this project is to identify a thermal resilience indicator to allow to assess and improve the resilience performance of the current building stocks to overheating risk caused by climate change events like heat waves. So let's delve into how cooling strategies can impact thermal resilience and energy efficiency in building design. To answer this question, we analyze a new passive office building located in Ghent, designed in compliance with current European and local legislation. The entire building was modeled in Design Builder's software, and the investigation focused on the two top floor office room. 4.1.6 is a landscape office room facing southwest, and 4.7 is a smaller single room oriented to the south with a higher window-to-wall ratio. Different passive and cooling strategies were analyzed using two medium-term heat waves data files. So, focusing on the HVAC system, heating and cooling are provided by a reversible heat pump. We examine three cooling scenarios. The first scenario explored involves unlimited cooling capacity to ensure comfort and maintain a set point temperature of 26 degrees. The two alternative scenarios with limited cooling power were also explored. The first with the pre-cooled air supply only via the R&D unit, and the third case that combine the pre-cooled air supply with a limited cooling by fan coil unit. All cases are combined with the possibility for the R&D unit to switch to free cooling mode when the outside temperature exceeds 15 degrees and indoor temperature is above 24. We tested 25 configurations under two heat wave scenarios. So we have totally 100 cases visualized in a Pareto chart. So this graph shows in x-axis the primary energy consumption and the y-axis overheating percentage. Each point on the graph corresponds to one of 100 combinations analyzed. And to visually emphasize our result, we use color coding for different strategies. So no strategy red, blue cooling, and natural ventilation yellow, and then we combine all the simulation, all the strategies. Analyzing the graph, we can observe that the passive strategies, so the passive measure alone, highlighted by the red circles, exhibit lower energy consumption, but overheating ranging from 7% to 70%. In particular, the result underscores how the solar factor alone can impact overheating, with external solar protection alone reduced overheating by 20%. Overheating value below 30% for passive solution are represented by natural ventilation, where the possibility of opening all windows and creating cross ventilation is feasible. This option is not always achievable and depends on the geometry. The light circles present solution with active cooling. Automatic sizing configuration allow to achieve overall comfort level, but lead to a clear increase in energy consumption. Active solution in which we limit the power cooling shows overheating exceeding 30%. The optimum solution showcased by the orange and green data points on this graph signify the synergy between shading, active cooling, and free cooling. This configuration maintains average consumption level ranging 120 kWh per square meters and keep overheating below 10%. This new graph compares cooling power and overheating. This data provide valuable insights. To achieve total comfort, a cooling power greater than 50 watt per square meter is needed. Relying on limited active cooling alone is insufficient, the red circle, and while the green circle shows that to achieve an overheating below 10%, passive and active strategies must be combined. The same graph highlighting the room type, so the landscape and the smaller, show how for the same case study, room geometry and windows ratio play a significant role. A 40% increase in cooling power is required to arrive to overheating less than 10. So to connect back to the project, we pose the question, what effect do different strategies have on the thermal resilience index? If we update the graph with the thermal resilience index set to degree hours 28, instead of overheating, we observe that during the heat waves with the most severe period, so 2051, is more challenging to achieve resilience. By defining the three resilience categories and highlighting the type of strategies, we can conclude that without any strategies, buildings are not resilient. So the red point here over greater than 250. To achieve a good level of resilience, the project must be designed by the reflecting and combining all strategies. So now not to the main focus, but we also asked, what is the cost of building resilience today to ensure comfort tomorrow? We performed a preliminary economics evaluation in real terms, no inflation adjustment, considering the future climate scenario. The chart shows additional investment cost needed compared to a standard compliant building built today. This enables stakeholders to make informed decisions about future-ready construction. So if we can see in this graph is that to be resilient, an additional investment of minimum 100 euro per square meter is required. If we compare the investment cost of the blue point here, in which use active strategies limited with the operating cost in the OPEX, the second graph, we can observe that this point exhibits an higher annual consumption. So the best solution remains a combination of strategies. So based on our analysis, we have arrived at the following conclusion. To ensure comfort during heat waves weathers, doubling the installed cooling capacity is necessary. The implementation of exterior solar shading proved to be significant in enhancing resilience to high temperature. Relying solely on passive strategy is insufficient to achieve optimal thermal comfort. It is imperative to combine passive strategies with active systems for effective result. While cross-natural ventilation offers excellent comfort with minimal energy consumption, but its applicability may be limited in certain contexts. The size of the room and windows have a notable impact on heating and cooling energy demands, and a minimal additional investment of 200 euro per square meters is required to effectively mitigate overheating risks. Investing today ensures resilient future-proof building capable of adapting to future climate conditions. In light of this finding, it is essential to note that our study focused on the worst-case scenario involving office facing south and southwest of the tops of the floor. So this is the worst scenario, with only 100 cases, a limited scope of our dataset. So to further enhance the robustness of our analysis, we recognize the need to expand our dataset to encompass a broader range of building types and orientation. And at at least the economic analysis is indicative, is a preliminary forecast, and will require for the detailed assessment in the future. Thank you for your attention. So I pass to Hilde for the Q&A. Thanks.